Our factor theorem, which is huge in algebra, says a polynomial f of x has a factor of x minus k if and only if f of k equals 0. So a polynomial f of x of degree n has at most n zeros. These are two properties we're going to need to know as we approach this section. Let's look at something called the completely factored form. This was the original polynomial I gave you. Remember the ugly coefficients in descending order? This has n real zeros. Okay? Say it has n real zeros, C1 through Cn. Each distinct real zero is listed, including those with multiplicity. So C3 and C4 may be the same, but I'm going to still list them as C3 and C4. I can rewrite this original polynomial as an times x minus c1 times x minus c2 times x minus c3 all the way down to x minus cn. In other words, if I know all the factors, I can factor this out completely, each one of these being an x minus ck as a factor, and the a to the n out front. Now notice this a to the n is the same as this a to the n. Let's see how this works. So again, knowing that the a to the n's are equivalent in the prior slide, we can write the completely factored form. If the leading coefficient of f of x is 12 and the only two zeros are 1/3 and 1/4, then the completely factored form is unique and can be expressed as follows. I have two zeros, 1/3 and 1/4, so that means there's factors of x minus 1/3 and x minus 1/4. And if 12 is the an is the leading coefficient, the 12 simply goes out front. So we can take just this bit of knowledge here and write the completely factored form of this polynomial. Now one thing we can also do, which we're not going to do here, is we can actually FOIL this and write it in standard form. Let's look at another example. I have the graph of f of x equals x cubed minus 9x, and I want to write it in factored form using the factor theorem. Notice this graph has how many zeros? It has 3 zeros. It crosses at -3, it crosses at 0, and it crosses at 3. Therefore, I have factors of x plus 3 corresponding to the 0 of -3, factor of x corresponding to the 0 of 0, and a factor of x minus 3 corresponding to the 0 of 3. So if I want to write this in completely factored form, the only other thing I need is the leading coefficient. If we go up to the original function, the leading coefficient is 1. Therefore, in factored form, the leading coefficient has to be 1 as well. So this is simply 1 times x plus 3 times x minus 3. Let's write the completely factored form of the polynomial. I'm given this function, f of x is 6x cubed plus 19x squared minus 2x minus 3. I know it's degree 3, so it has at most 3 real zeros. I'm actually given all 3 real zeros, -3, -1/2, and -1/3. So if I want to write this out, I know f of x equals a, my leading coefficient, times x minus c1, x minus c2, times x minus c3. I know I do not have to go any further because I know that at most there are 3 real zeros. Again, my leading coefficient in the original function was 6, so the leading coefficient on the factored form is 6, so this is 6 times x plus 3 times x plus 1/2 times x plus 1/3, and that is the completely factored form. Let's try something a little bit more difficult here. It says the polynomial f of x equals 2x cubed plus 5x squared plus x minus 2 has the 0 of -2. Express f of x in completely factored form. Notice in this case we're only given one of the possible 3 real zeros. So what we're going to do is we're going to take this -2 and we're going to use our synthetic division we learned in our previous section. If -2 is a 0, then x plus 2 is a factor. I will use the -2 out front, and the numbers that go on my top line are 2, 5, 1, and -2. And we start by bringing down the 2. 2 times -2 is -4. 5 minus 4 is 1. 1 times -2 is -2. 1 minus 2 is -1. -2 times -1 is 2. -2 plus 2 is 0. Notice this 0 matches up with our factor theorem because this says that f of -2 is 0. So if I go to factor this now, -2 is a 0, so this is x plus 2. and then this is what's left over, 2x squared plus x minus 1. 2x squared plus x minus 1. We should be able to factor this. It factors to 2x minus 1 times x plus 1. This piece here is what gives us a little bit of difficulty and we have to address. Okay? Notice our factor theorem says that all factors are the form x minus c. In other words, the leading coefficient is 1. I have to get rid of this 2. Okay? In fact, I just want to highlight the 2. I don't want to highlight anything else because that is the part that we have to address. I'm going to pull this 2 out here, and that's going to leave me with x minus 1/2. So now I have the 2 out front times x plus 2 times x minus 1/2 times x plus 1. This matches up with our factor theorem because our leading coefficient here is 2. Leading coefficient there is 2. Let's look at another example. It says use the graph below to write the polynomial in completely factored form. We know it's an odd function because the end behaviors are opposite. And we know there's 3 zeros, so we know it's at least degree 3. It has zeros in -1, -2, and 1 based on the graph. So if I write this function, this is f of x equals a times x minus c1, x minus c2, and x minus c3. So f of x equals a times x plus 2 times x plus 1 times x minus 1. Now we still don't know what a is. We cannot assume that it's 1. We have to actually calculate it. We have another point on this graph. We have the point 0, -4. We need to find a point other than the zeros to plug in. So we're going to plug in 0 for x and -4 for f of x. We get -4 equals a times 0 plus 2 times 0 plus 1 times 0 minus 1. This becomes a times 2 times 1 times -1, which is -2a, equals -4, so a is 2. So my completely factored form is f of x equals 2 times x plus 2 times x plus 1 times x minus 1. Our last type is going to be rational zeros. Not all zeros come in nice little numbers. Some of them come in fractions. So we need to find out how to find all the rational zeros. All rational zeros are of the form p over q, and p is always a factor of a0. It's always a factor of the constant term. And q is always a factor of an, which is the leading coefficient. So let's see how this works. I have this polynomial f of x equals 6x to the 4th plus x cubed minus 26x squared minus 4x plus 8. I want to write it in completely factored form. I need all the rational zeros. So p is a factor of my constant term, the 8. So the factors of 8 are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. The q are all the factors of the leading coefficient, which is 6, which are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So any rational zeros must be of the form p over q. So I simply write 1 over 1 is plus or minus 1, 2 over 1 is plus or minus 2, 4 over 1 is plus or minus 4, 8 over 1 is plus or minus 8. Let's go into the next one. 1 over 2 is plus or minus 1/2, 2 over 2 I've already accounted for, 4 over 2 I've already accounted for, and 8 over 2 I've already accounted for. 1 over 3 is plus or minus 1/3, 2 over 3 is plus or minus 2/3, 4 over 3 is plus or minus 4/3, 8 over 3 is plus or minus 8/3. 1 over 6 is plus or minus 1/6. I've already counted for 2 over 6. It's the same as 1/3. 4 over 6 is the same as 2/3. 8 over 6 is the same as 4/3. So here's a list of all my potential rational zeros. That's a lot to account for. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and double that, we end up with 22. Actually, that's 10. We went up to 20. That's still too many we want to check, so let's start seeing what we can do. This is a long list. Easiest one is to plug in your whole number. So let's plug in 1 and -1. We plug in 1 and -1 into the function, we get -15 and -19, which don't work. Those do not give us zeros. However, when I plug in 2, I get f of 2 is 0. So we want to thin this list out some. So we plug in f of 2 is 0. Let's do our synthetic division. Our 2 goes out front. Our 6, 1, -26, -4, and 8 go across the top. We drop the 6 down and we multiply. 6 times 2 is 12. Add to 13. 13 times 2 is 26. add to 0. 0 times 2 is 0. Negative 4 plus 0 is negative 4. And finally multiply, we want to put 0 here. So the factor is x minus 2, and we're left with 6x cubed plus 13x squared plus 0x minus 4. We're going to do the same thing again. We're going to find the p's and q's. Notice my p's and q's are different because I'm not using 6 and 8 anymore. I'm using 6 and 4. So your p's are different, plus or minus 1, plus or minus 2, plus or minus 4. Your p over q's actually shrink. We know some of these don't work because we already tried the 1 and the negative 1. We've already tried a positive 2. So let's come back and try a negative 2. When we come out with a negative 2, we actually find out that this does work. That negative 2 does make this function 0. And the interesting thing about when we want to plug in, we don't have to plug into this whole function. All we have to do is plug into this new factored part back here, because we know negative 2 will not make this piece here 0. So let's do synthetic division again. Negative 2 into this 6x cubed plus 13x squared minus 4. That's the part we're going to worry about. And again, this winds up with 0. So this whole function now becomes x minus 2 times x plus 2 times 6x squared plus x minus 2. This we can plug into our quadratic, which you should be able to master by now. And we get x is 1/2 and x is negative 1/3. So these are our factors: x minus 2, x plus 2, x minus 1/2, x plus 1/3, and we already know our leading coefficient is 6. So we should be able to factor any polynomial that can be factored over the set of rational numbers.